Welcome, calculus students. This is the area volume review sheet 1. I'm going to solve each problem for you, and I'm also going to work with the graphing calculator. So first problem here is to find the area. And if you remember, area is, we're going to integrate, which is adding an infinite number of rectangles, right? So we'll draw a rectangle as I've taught you to do. And just draw some random rectangle. Remember, there are many of these rectangles. Okay, it's a terrible rectangle, but you get the idea. And of course, the base here is dx, an infinitely thin base, right? And of course, our height here, and this is what you always struggle with, our h here, the height from here to here is the distance between these two functions, right? And the distance between these two functions is just upper function minus lower function. If the lower function is the x-axis, then it's just the upper function, but it's technically the upper function minus 0, right? So again, we're taking a differential area, an infinitely thin area, and we're saying that that's just base times height, the area of a rectangle, right? So the base is dx, which we'll put at the end, and then the height is this height of the rectangle, which in our case is f minus g, right? I'm just going to leave the f of x off just to make our lives easier, right? It's f of x minus g of x. F minus g. And then all you got to do to find the area of all the rectangles, meaning all the shaded region, right? All of the shaded region here, is to integrate both sides, right? So area equals the integration of this, right? F minus g dx. And of course, it's from what to what? Well, it's from -2 to this intersection point here, which we'll have to find, right? I think that's -2. We'll check that too, right? So it's -2 to some intersection point, which we'll have to find. Okay. All right. So that's the theory, right? So let's go to our calculators. Now we're going to have 4 parts for this problem. So it's going to definitely be to our advantage to enter these functions so we don't have to keep doing it over and over again, right? So ln x plus 3, we'll put f first, right? ln x plus 3. You don't really need to close the parentheses, but we'll do it anyway. And then g of x is x to the 4th plus 2x cubed. 2x cubed. Okay, so there's our 2 functions, f and g. Let's take a look at with their intersection points. That does match our graph pretty nicely here. If you want to zoom in a little bit, right, we could zoom in once. Probably help us a little bit. Okay, not really. So anyway, we're going to do second, calculate intersection points. I'm assuming that first one is -2. It looks like it is. First graph, enter, enter. We only have 2 graphs. We don't have to worry about that, but the guess is important. We want to go over to where we want to know. So there it is, -2. That just confirms it. We'll do it again. Second, calculate intersection, number 5. Scroll all the way over to here. Oh, I'm sorry. First curve, second curve, enter, enter. And then our guess is over here somewhere. Just have to be close. Okay, and that is 0.7819751. We're going to keep at least 4 decimal place accuracy here because we need 3 decimal place accuracy for our answer. So I'm going to write that. I'm going to write x equals 0.78198, right? I'm going to round that 7 to an 8. So that's 5 decimal place accuracy. I think it's a little better. Okay. And I can store that in my calculator. I think I will. All right. So I'll just clear my calculator here and I'll just type it in. So 0.78198. Now you could have been more accurate here, right? I think it was 7.6 or 7.5, whatever. So you could put more here because we're going to store this. We don't have to keep dealing with it, but 5 is plenty. So I'm going to type that in and then I'm going to store that. Or actually, let's see if I have to press enter first. Okay. Yeah, let's delete that. Okay, so let's press enter so it's there. Okay, now we're going to store it in alpha A. Okay, and so A has that number when we need it later. Okay. So we're going to integrate, and I don't want to call this x, actually. I probably should call it small a, right? Because that's what I stored it in the graphing calculator is. Okay, so anyway, find the area. It's going to be the integration from, right, f minus g, which we already have in the calculator, dx. We want to put a parentheses around that. And it's from -2 to a, right, which is that decimal there. But I don't need to write that anymore because once I've written this, right, even on the AP exam, once I've defined a variable like this, I can keep using that variable. It kind of looks like a 0, so maybe A wasn't your best. Maybe B would have been better. But as long as you're neat, it's harder for me on the screen here. You can use that letter A, and you're ready to go for the rest of the problem. Same thing with F and G. They've defined F and G, so I never have to write this when I'm solving this problem on my AP exam. In other words, I don't have to, not solve it, but I don't have to represent these functions with their algebraic expressions. I can simply just represent them by their names. And same thing with the letter A, because I have to find the A throughout the rest of the problem. So we don't want to make busy work for ourselves and waste time. Okay, so let's put that in our calculator, right? So we're going to integrate. So math, FNINT is number 9. From 0 to A. Remember A, we've stored A, so I'm going to put alpha A. Okay, 0 to A, and it's going to be F minus G. Now, to get F and G in there, we're going to use the vars key. We're going to use the y vars. Let's move one to the right. Function number 1. And then we're going to put y1, that's F, right? Minus y2. Same thing again, just do y2. Vars, right arrow, number 1. y2 is number 2. There it is, and put in dx. Okay, got to put in dx, and then enter, and we're good. Okay, so that is the area, 0.707. 0.70. Now, you can round it or truncate it. I like to round it because it feels more natural to me, but you need 3 decimal place accuracy. Better to put 0 point, by the way, I didn't do that, but 0.708, put 0.708 for your area. And there's no units here, I don't have to worry about that. It wasn't a word problem. So just find the area, that's the area. Okay? Yeah, that can't be right, right? There's something wrong there because I must have done 0. Oh, I did 0. Okay, sorry, we got to do -2. I don't know why I did 0, but I can tell it's not right, right? Because you can see, for example, that this rectangle here, this square here, right? That's an area of 1, right? So I'm guessing, and there's an area of 1 here, almost, not quite, right? I'm rounding here. That's 2. This is, you know, a half, maybe another. So you're looking for an answer around 3 or 4. You can just tell by here. So this is a great lesson in recognizing that you've made a mistake, because you should roughly know what the area of this bounded region is, right? And of course I made a mistake here. I put 0 instead of -2. I don't know why I did that. So probably from habit from class. So let's go back and do math. Actually, I can edit that. I should have done that. Let me show you that, right? Let's see if I can. Okay, I can go up arrow here, up arrow again, hit enter, and it will re-edit that as if, so I don't have to retype all that in. That would save me a lot of time. So there's another great lesson in, if you realize you made a mistake in your integral, you can arrow up to the previous integral that you had, hit enter, and then just make a small edit rather than typing the whole thing again, which I almost did. So -2, and I'm sure that will give us an answer around 3 or 4, somewhere between 3 and 4. Let's take a look. Perfect, right? That's exactly what I expected. So yeah, I did that on purpose. No, I didn't. I made a mistake, but I caught my mistake because it just didn't feel right. And then I'm going to go 3 decimal place accuracy, 4. Okay. All right, so a couple of great lessons here. One is know roughly what your answer should be, or at least know an answer that makes no sense, right? Point whatever we had before, 0.707 is a terrible answer, right? Because I can see it's more than 1 clearly, and it's something in the 3 to 4 range. And then the second great lesson here is using the calculator is never retype the entire integral or whatever calculation you're working on. Use the up arrow key, hit enter, right? Up arrow, hit enter when you get whatever selected that you want to work on, and then just edit that from there. Okay, that's great. Let's go to the next slide. All right, find the volume of the solid formed by revolving the area enclosed about y equals -2. So let's go back to the diagram to look at that. So y equals -2 is way down here, right? Way down here. And because I doubt this goes as low as -2, right? And again, because this line does not, this lower border of our region does not lie perfectly flat against this revolution line. So because of that, I know there's going to be air, right? So we're going to basically take this thing and revolve it like this. And, you know, if you wanted to do like, it's hard to do with this one, but if you want to do a mirror image, it would look something like this, right? Something like that, right? And you could see our slice, right? So we talk about our slice, our cylindrical slice, our cylinder, and it would look something like this, right? Yeah, it's a terrible, terrible picture here, but you get the idea. This would be the edge of a coin, right? We talk about a coin in class, and here would be the rounded part like this. Again, it's not a great image. Probably use the tools to do this a little better. Yeah, maybe I will. It's worth it for the first one, right? For the other ones, I don't know if I'll do it, but okay, take a nice rectangle like this, right? And then let me see if I can start from the center. No, that's not terrible, not great. Okay, and again, just so it's clear, this is the edge of the coin, right? And there's many of these coins, right? There's a larger one as we come over, you know, in this direction. There's gonna be a larger one, right? There's an infinite number of them, and our radius, of course, is from our center line, right? Right to here, right? Our center line to here. So there's my outer radius, right? My R. That's the radius of the coin. Now, again, this is just the volume of everything, including the air inside, right? The gap. But we're assuming only the outer function and y equals -2 to be the border here, right? In other words, the solid figure before I remove the air, right? Okay, and of course, just like before, right? I'm going to go to the other screen, but you can see what I'm going to write here. R is going to be what? The upper function here, right? F minus -2, right? That's going to be my radius here. Okay, so if I think about this coin, right? I'll attempt to make another coin here. Right, pretty terrible, but you get the idea, right? So if I think about this coin here, right? That is F, the upper function, minus the lower border, which is -2, right? So F minus -2, right? That's y equals -2, that's F. So this is equal to my radius, okay? My outer radius. Now there's an inner radius that we have to deal with, right? But that's my outer radius. Okay, so the formula for a infinitely thin coin, right, or infinitely thin disc or cylinder, right, dV, is of course pi r, right, squared, and then the thickness of the coin. But the thickness of the coin is dx, right? This is an infinitely thin thickness dx here. Okay, I'm gonna turn this down a little bit, right, dx. Okay, and in here is the radius, right? This is my r, right? And of course, my r in this case is F minus -2. So I'm just going to write F plus 2. But remember, it's lower, it's minus the lower function. It's just that there's a double negative here, right? So it's really F minus -2 squared, okay? And then I'm going to integrate that. And I'm going to put the pi outside the integral, but I'm going to integrate that. And again, it's going to be from 0 to a. I'm going to double check that because I don't see it in front of me, but I think it's 0 to a. And that is going to give me my total volume. And there we go. Okay, but that's only the outer, you know, the solid shape. In other words, the answer to the problem that we want, the shape that we want, the volume that they're asking us for, and the extra air. So we have to subtract the air, right? And then the air volume is going to be the exact same thing, right? Pi r squared. And then thickness, right? But if I go back a slide and look at that, so the air volume is going to be a different cylinder. It's going to be, right, this little green cylinder here, right? There's the air right there. Not a great cylinder, but you get the idea, okay? And of course, over here, the air cylinder would look like this, right? It's bigger. That's why we have to write it in terms of x, right? Because it's constantly changing sizes, and we need to add up all of these coins, not just one sized coin. That's why we don't use a constant for the radius, right? We use the in terms of x, the algebraic expression. And again, what is the radius of this green coin? You can do it here or over here, doesn't matter. It's the lower function minus the revolution line, right? So the lower function. So this is G minus minus 2, right? Sorry about the, all right, it's not clear to see, but G, this line here is G minus negative 2, right? Or G plus 2. So that's the inner radius, right? And we're going to subtract that volume. So this is G plus 2 because it's G minus negative 2, right? That inner radius in our green smaller coin. It's not that it's necessarily smaller. I guess most of the time it is, but let's see. In our coin here is the G function, right? The upper function minus the lower function, okay? And that's my R2, right? R2, the green R, and you call this one R1, R2, whatever. That's what the, so again, you can do these separately. Again, I have to integrate this, right? I have to integrate this. You can do these separately. Okay, and this is the air that's the air volume. I'm not going to fit that there nicely. This is the total volume, right? But we want the volume of the solid, right? So the volume of the solid is, of course, the volume of everything minus the volume of the air. Again, sorry, air didn't fit here nicely. It's little right here. Okay, that's air. Now, you can do these two separately and extract their thing, but the way the book does it and the way that the AP solution guides do it, because you're probably checking those, right, is it does it in one fell swoop because there's everything common here, right? You've got this, you've got the dx the same, you've got the same integral, right? The same integral, the same dx, you've got the same pi, right? And then you've just got what? The only thing different is these two things squared. So you can make a single integral, and that's what the book and the AP solution guide likes to do. I'm not a fan of it because it gets confusing and kids tend to subtract the two and then square them, you know, so it's a little messy. So, but I'm going to do it because that's how you're looking at the solution probably. So it's 0 to A, and then it's just the 2r squareds, right? So it's F plus 2 squared minus G plus 2 squared. And then, of course, the whole thing is dx, right? Which technically needs a bracket here. Okay. So that's how I'm going to type it into the calculator because it's just a little quicker. It is how the book solves it, right? It's R2 squared minus R1 squared. But be careful. A lot of kids put this all together and make one single squared. And that, you know, that leads to errors, all right? But basically, that's it. And you can leave it, and you can write it just like this, by the way. You know, again, notice I'm not using the algebraic expression for F and G because it's just a time waste, as well as not writing the letter A over and over again. Okay, so let's go and get this done. All right, so math. By the way, if they said write but do not evaluate, right, we're done. But they didn't. So math, I must have hit the wrong button. Okay, math 9. Okay. Oh, I know why, because I'm in here. I don't want to be in here. Math 9. We'll multiply the answer by pi at the end, right? Just to save ourselves the hassle here. Negative 2, I don't want to make that mistake again. Negative 2 to A, alpha A. This could be a little complicated here, right? So I'm going to leave that parentheses for the dx, but then I need a new parentheses, and I'm going to do F, right? I'm going to do this quicker so because you know how to do this. All right, F plus 2, close parentheses, square that, okay, and then that's the outer radius, right, and then the inner radius for the green cylinder, the air, is parentheses G, again, vars, y vars, function 2, plus 2, squared. So again, I'm doing this like they do it in the book and like the AP solution guides do, so you can understand it, but you can do this separately as well. Okay, that should work. If I did everything correctly, I think I did. Double checking it, looks good. This is much harder. Like, you can't look at this and guess what the volume is, right? It's just a mess. So it's harder to know if you did something wrong. So you just got to be careful here. All right, anyway, the volume equals 14.393. Remember, 3 decimal place accuracy, super important. Okay, let's move on to C. The region enclosed by the graphs of F and G is the base of a solid. All right, so we're no longer we're doing a revolution. This is the base of a solid problem. Cross sections taken perpendicular to the x-axis. That's important. So we know it's a dx problem, right? Our squares. All right, so our volume formula for a 3D square, aka a prism, right? So a 3D square is going to look like this. I shouldn't say a 3D square, right? That implies a cube. It's really a piece of toast, right? And so we're going to get base. That's what's lying on our surface, right, on our shaded region, H, and then this sort of little dx here, the thickness, right? And so, right, it's super easy. We're going to take a differential volume. We're going to take a one slice, an infinitely thin slice, right, is nothing more than base times height times thickness, right? Times thickness, right? But we're going to integrate that, of course, to get our regular volume. And in our case, it's going to be the same thing. I believe, I'm going to double check, but from -2 to A. Okay, and that's going to give me my total volume. So the key is, right, what's the dimensions of the slice, right? So if I go back to slide 1, and I erase all this, because there's no more revolution, so this doesn't apply anymore, right? So there's my area, my base of my solid is this enclosed region. And basically, I'm going to lay down a square, right? So here's the base of the square, and I'm just doing one of them. There's many of them, right? So I'm going to take a square like this, right? That's the base of the square. And then it's going to come out of the blackboard like this, right? It's hard to do a 3D here, of course, obviously, right? And that's the shaded is like the part that's facing you, right? And then there's a little bit of thickness here. Okay, so, you know, it's hard to draw 3D here. If you were looking in a helicopter view directly overhead, right, you would just see a thin line, right? You would just see a vertical thin line because it's coming out of the blackboard, right? It's coming straight out of the blackboard, right? So the important part, though, right, is that from here to here is the base of, well, a little to the right of there, but, right, that's the base of this piece of toast, right? It's a base of this infinitely thin piece of toast, right? And that's just F minus G. So we know that's the base of my square. And of course, because it's a square, the height is also the same, right? So if we go back here, right, it's real easy. This base right there is just F minus G. And because the height and the base are the same, because they told me it's a square, right, then this is, of course, F minus G also. All right, so this base is F minus G, this height is F minus G, so it's just F minus G squared. So the final answer for this is the volume equals, from the integration from -2 to A. Notice there's no pi here because I'm not doing a revolution, I'm not doing a cylinder, right? So it's -2 to A, base times height, which is just a duplication of itself, right, multiplied by itself. And then the third dimension, dx, that's my thickness, right? And that's it. So we can do that really quickly. We can do that really quickly. F and I and T from -2 to A. Luckily, all this is still stored in here. Oh, I hit the wrong button. Sorry. -2 to A. I meant to do alpha A. And then our classic F minus G, but it's going to be squared. So, right, I need another parentheses here. It's going to be squared. So I'm going to do my y vars minus y vars, and then of course go outside. Oh, I got to go out there. Oh, I didn't close parentheses. That's what the problem was. Then I'm going to square that, and then I'm going to put a dx in here. Again, not easy to guess what this would be, so we're just going to have to trust that we did the right work here, and we get 5.34. That seems right. Time will tell. 5.340. 3 decimal place accuracy. I'm going to use rounding. Whoop, my pen went out of control there. Sorry. And that's my volume. Okay, base of a solid. Again, it could be any shape, right? Well, actually, I think the next question maybe is another shape. So let's take a look. Yep, same as C, but with semicircles. Okay, so the only difference is I have this sort of 3D, like a taco, right? Like a taco shell, 3D semicircle, right? That's the only difference. But we still have, you know, and I'm just roughing this there, F and G. I still have, it's bordered by F and G. over the same -2 to a, right? So nothing's really changed. So the base of this semicircle here, and I want to be careful when I say base, right? It's technically a diameter, right? So the distance from here to here is f minus g, as we used with the square. So the square, or really the 3D prism, right, had a base of f minus g, and so does the diameter of our cylinder here. All right, so be very careful, right? The differential volume, meaning the volume of one of these taco shells, these infinitely thin taco shells, right, is of course a half cylinder. So it's a half, right? It's a half cylinder, which is pi r squared, and then the thickness, right? Because it's 3D dx, okay? So it's a half cylinder pi r squared dx, okay? And of course, to get the actual volume, I want to integrate this. And I'm going to keep that 1/2 and the pi outside of this integral. And it's going to be -2 to a, -2 to a. And this is our radius, not diameter. So unfortunately, f minus g is a diameter. But I actually only want this. I want the radius, right? I want r. So the radius is half of that diameter. So it's f minus g over 2. Now you can just put this in exactly like this, but you can also realize that if you squared this, right, you're going to get f minus g quantity squared over 4 and pull the 4 out. And that's what we do in class, right? So I'm going to do that. So I'm just going to write 1/8 or pi over 8. Right, so I pulled out a 4 from this because this is squared. Pi over 8, integral -2 to a. Oh, I just realized what we did in the previous problem. I forgot to multiply by pi, I think, on this volume problem back here. Remember we said we're going to multiply this by pi at the end and we didn't? I realized I didn't do that. Sorry about that. Times pi, right? I'm going to leave that to you to figure out because this is, you know, you can do that easily in your calculator. But I remember we did this whole integral. We got 14.393 and I forgot to multiply by pi. Just remember that. Very dangerous. So be careful when you do it yourself if you don't put the pi in the calculator. Okay. Glad I cleared that up. All right. So back here, f minus g squared dx. Okay. All right, let's see if we can't do that a little better this time. So this is what you should have done in the other problem, right? That I didn't do. So I should have done pi, and before I should have just written pi. Of course, in this problem, it's going to be pi over 8, right? And then times, and now do the math f on I and t. This way you don't forget it, right? So it was another great lesson in this video is, and again, great lesson because I keep making mistakes, but it's a great lesson to put this in the beginning. Don't wait till the end like I did before and then forget to put it back in. Okay, so it's going to be pi over 8 times the integral f on I and t from -2 to a. We still have the same a in here, alpha a. And we still have the same f and g. Again, it's going to be squared, so I need the parentheses here. Be careful. Vars. Oh, I did something wrong. Sorry. Clear it up. Vars, y vars, excuse me, functions y1 minus y2. Now notice we're not dividing it by 2 because we already took care of that. We pulled it out in the beginning, but you might have had a divided by 2 here if you didn't make this pi over 8, if you left it as pi over 2, and then dx, and this should be the right answer. Okay. Kind of small, but that makes sense because these are, well, I don't know. Well, I hope it's the right answer. Looks a little small, but maybe the taco shells are kind of low. And there we go. Okay. So again, base of a solid with a semicircle. Remember that it's half pi r squared dx, the thickness, but the diameter is f minus g, not the radius, so you have to divide that by 2, and that was the whole key to semicircles. All right, next problem. Okay, now if you have a calculator, typically you might on this, but you might not, right? So you should know these functions from pre-calc, though. E to the x, of course, looks like this, and every exponential function passes through this anchor point, as we call it in class, 0, 1, right? And then x to the third is like that kind of essy thing like this, right? And it goes up like this. Now, where does that hit is the key, right? So this probably would be a calculator problem. They're not going to make you do this. So let's do it with a calculator. Okay. So let's get rid of our two functions here. If you didn't do this with the calculator, I'm not sure. Anyway, let's just do it with the calculator. And this is the base of a solid problem, by the way. So we're just looking for the region that's bounded by these two functions. Oh, actually, and the y-axis. I didn't look at that. So it's going to be bounded here, right? So it's going to be something like here, and then everywhere until these guys intersect, which, somewhere we need that x value. We'll call it b this time. Okay, we need that b value. That is the x value of the intersection, but we know it's going to be from 0 because it's saying the y-axis is also a border. Okay, so let's go to y equals. We'll put in e to the x. And for y2, we're going to put in x cubed. Okay, let's take a look. And there we go. There's an intersection point. Again, there's no intersection over here, but that's why they added the third boundary of the y-axis. But we got to find that intersection point, so we're going to do second, calculate intersection. First curve doesn't matter. First curve, second curve, just press enter, guess. Again, doesn't matter because there's only one. But if you want to make you feel better, get close to it, press enter. Okay, there it is. So b equals 1.85718. Let's go a little further this time. Again, as long as you go 5 decimal places, you're fine. All right, and let's store that. So I'm going to clear my calculator. I'm going to type in 1.8. I may not have to do this, right? If this is the only problem, if there's not another part to this, right, which typically is not going to happen in the AP exam, there'll be multiple parts. But if there's not, I really don't have to go through this work. I could have just typed it in once. But it's just good. Whoops. It's good habit to do that. So I'm going to press enter, and I'm going to store this into B. So the stow key, alpha B. Okay, there we go, stored in B. Let's do the, so the cross sections are perpendicular to the y-axis. Oh, we're going the other direction. I'm sorry. The cross sections are perpendicular to the y-axis. This is not perpendicular to the x-axis like we normally do. And they're rectangles with a height equal to 6 times the length of their bases. Okay, so it's a little more complicated, right? So let me get the selection tool and talk about this. Okay, but this is basically our shape. So yeah, not a terrible picture of our shape. Okay, so here's the problem, right? We have to go like this, right? Our rectangles are going to look like this, right? They're going to look like this. So that makes it a pretty complicated problem. Those are my rectangles, and the problem is that it's not just between the two functions, because down after you pass this number here, it's different. The rectangle is now bordered by this x cubed and the y-axis, right? So let me say that again a little clearer. So let me get rid of all this. So if I start drawing rectangles, now I'm drawing segments because they're super thin rectangles, right? But if I'm drawing rectangles, and the key here is perpendicular to the y-axis, right? Not the x-axis like normal. So my first rectangle goes from that green line, well, not my first one, but the first one I'm drawing, from that green border, right, which is the y-axis, to here. So it's blue minus green. This one is also blue minus green, right? But as soon as even at that intersection dot there, right, it's fine. But now the next one I draw here, and remember, there's an infinite number of them between here, but I'm drawing the fourth one that I drew here. That is between the cubic function and the e to the x function. See, so I've got to do two integrals here. This is a rather complicated problem. All right, so based on that overview, let's talk about one more thing. You have to look at this problem, right? You have to look at this problem with your head turned to the right, because this is going to be your up axis and this is going to be your down axis, right? So you have to turn your head, you have to look this way and say that this is the upper function when you're turning your head to the right, and this is my lower function. Because we're going to be doing a dy problem, right? If this is one of my rectangles here, right? It's my rectangle here. This is dy. This is a dy, not a dx problem. And therefore, I need all my functions in terms of x, right? And because this is the x-axis, that's like what my y-axis used to be. It's my vertical axis, right? In other words, turn your head to the right 90 degrees, and that is your upper, and then the lower is below it. So you need to get that upper and lower perspective here. So I need a lot of things. First of all, I need to convert these two functions. So obviously y equals e to the x. I'm going to natural log both sides. And I get x equals natural log of y. And then for x cubed, I'm going to cube root both sides, right? So x equals the cube root. You don't have to worry about a plus or minus here. It's an odd power, right? We're good. Okay, so there are my two functions in terms of y, right? Because it's a dy. I needed to integrate a y with respect to y, right? With a dy here. So I know it's a dy because these rectangles are going this way, so their thickness is this very small change in y, right? This dy. So everything changes, right? I have to change my perspective that my head is turned to the right 90 degrees so that x is upper, right? The positive x-axis is upper, and the lower x-axis, the negative x-axis, is the lower function. I have to turn my functions to be x equals, aka in terms of y, because my thickness is dy. All because of this, right? All because they said the cross sections are perpendicular to the y-axis. Okay? Now, I still haven't done my volume yet. I know that my volume of each one of these 3D rectangles, right, prisms, really, the rectangles with a height equal to 6 times their base. So I'm going to have, right, of course, it's base times height times thickness, which is going to be dy. Okay? But I don't know what my height is. I do know what my base is. Right? We're going to upper minus lower function. We're going to talk about that in a second. But I don't know what my height is, but it says the height is 6 times the length of the base. So I can just replace the height with 6b. Right? The height is 6 times the base. In other words, coming out of the blackboard pretty high. So there we go. That's my volume formula. All I need to do is figure out what b is. Of course, I'm going to integrate both sides and what I'm going to integrate them to. And I have to do 2 integrals, right? I talked about this before. So that's a little bit crazy. So I'm going to first do from here to here, right? All of these. And the upper function is this cubic function, which is now a cube root function, right? Because I had to look at it from the perspective of x, in other words, in terms of y. So it's this upper function minus 0 because that's the equation of the y-axis, right? It's x equals 0. The y-axis is x equals 0. So that's my lower function, and this is my upper function. Okay? So that's the integral. Now be careful. The y's are changing. I'm not going this way. I'm going up and down. So y is changing from 0 to 1. So the y values are going from 0 to 1. All along this, we're going from 0 to 1. So as long as y is 0, anywhere to y equals 1, I'm using the rectangles that you see here, all of these rectangles that I'm shading here. They're all blending together, right? But those are all rectangles. They're, prisms, rectangular prisms, actually, with an infinitely thin dy. Okay? So those are upper minus lower. So upper minus lower, upper minus lower, okay? Upper minus lower. So that is upper cube root of y minus lower, which is 0. So, I don't have to really write this. And of course, that's dy, okay? And that's the volume of some of the solid formed, right? The other part of the solid is up here, right? The other part of the solid is these again, we're helicopter view of these prisms, right? These are infinitely thin prisms, rectangular prisms. Okay? Those guys, which goes all the way from 1 to the intersection of these guys. By the way, this is no longer valid because why was this not what we want? That is the x value of the intersection. I need the y value of the intersection point, right? In other words, here I need I know it's 1.8, something, ... comma, I need to know what that is because I'm integrating dy. So I'm integrating from 1, the y value, to whatever this y value is there. So that makes the problem even more difficult. So let me slide away some of this stuff over here. So plus 1 to I'm not sure yet, right? And then the upper functions are changing. So, oh no, I'm sorry, the upper function is still the same, but it's cube root of y, minus the lower function, which is now this blue, right? Which is the blue ln of x, I'm sorry, not ln of x, ln of y, of course, ln of y, because it was e to the x, okay? dy. All right, so our last job is to find this this b, which I'd stored before, which was a waste of my time. I really need to do the y value in the intersection. So really quick second, calculate intersection, first curve, second curve, guess is there. We don't even need to guess. So it's 6.4057. Let's do that. Okay, so I've got to change my b. We'll call it c. This way we're not confusing ourselves. We'll call it c. Okay, so my letter C is going to be 6. I got to change the pen thickness again. 6.405. What do I want? 67. 67. Okay. All right. Okay, so well, again, I really don't need to do this because I'm only going to use it once. So we're not going to bother doing this. Okay, so I'm just going to I don't want to write it multiple times, so I'm going to put C here, right? And that's okay, as long as you've written it once here and defined it, you can do that. Okay, so let's type this ugly mess into our calculator in one fell swoop, which I think I'll be able to do. So let's do math, 9. Okay, so that is going to be 0 to 1, because that's the y value of the, where the y-axis intersects e to the x, right? And then it's going to be cube root of y. I'm going to do math, cube root, number 4 of y. Now you're putting x in because the calculator won't take y, right? But you understand it's independent, and the calculator doesn't know any better. As long as this 0 to 1 is the y values, it doesn't matter if you call this x or y, as long as you're using the right functions, right? So don't be confused that I'm typing x in here. It's technically y, but the calculator doesn't know it. And minus 0, I don't really need to write, but if you want to write it, minus 0, okay, I'll write it. And then, of course, dx, even though it's a dy problem, because all you have to do is make sure that this x here is matching that x. That's all the calculator cares about, right? And that's it for that. Okay, and then plus the integral, so math, f and I and t, of 1 to c, which was 6. And again, I didn't bother typing this in before because it's only going to be one time. 0567. But definitely 5 decimal place accuracy there. And then it's going to be cube root of x again. Now, I didn't put these in the y vars, obviously, because I had to graph it the other way. I could have gone in and put these in like 3 and 4, right? y3, y4, but I'm only typing them in once, not the end of the world, or maybe twice here. Okay, and then of course math for cube root of x minus ln of x. Now carefully, you got to close the parentheses for the ln, and then you've got to close the parentheses for, well, I guess the parentheses are already there for the dx, so we're good. Yeah, it should take care of itself. Okay, I think that's right. And I'm going to press enter, and I get 2.43. That's probably right. I might have made a mistake, but 3, 1. Well, no, sorry, 2. So I can, well, I could truncate that. That wouldn't be wrong, right? That wouldn't be wrong. On the AP exam, they accept that. I will accept that. But let's put a 2 there, just because I like to round. It feels better. And that's my volume. Okay. Pretty tough problem because I had to write 2 integrals. I had to convert all my functions in terms of y. In other words, x equals something with a y in it. And then I had to write two integrals because the regions are not bounded by the same thing depending upon my y values. I had to find a different intersection. I had to find the same intersection point, but I had to find the y value of the intersection. A lot going on in that problem. That's a great problem for your test tomorrow for my AB students that I'm making this video for. Okay, this is the same exact thing. See, I should have put these in the calculator, but it's an equilateral triangle. So I'm not going to go through this whole problem for time's sake because my video is going to run on too long, but I will show you what you need to do. So it's going to be the same thing. It is perpendicular to the y-axis too, making the problem nasty. But all I want to do is show you how to figure out the equilateral triangle, right? So here's the equilateral triangle. I'm going to do the green section, which was the upper one. But again, this was the cube root function, I think, up here, and this was the e to the x function here. Again, converted, that would be ln y, and this was cube root of y, right? X equals. Okay. So I'm not going to go through the whole problem, but I'm going to talk to you about how to do the problem, right? So again, you're going to have two different regions. So it's going to be this minus this, or it's going to be the other one, this minus 0, right, for the other region. But regardless of that, I just want to talk about this. So for this 3D figure, right, the key is you got to figure out what this height is. So this is the base, and that's no problem. That's the difference between the functions, depending upon where we are in our two integrals, right? And of course, there's a thickness here, and that's our dy, right? It's our dy. So it's like a piece of shrimp toast. So this b is our base. That is the upper minus lower, which will vary, right? But the point is that to get the height in terms of the base, we've got to do some special right triangle stuff, right? So that's a terrible, I know. So let's make up a number. Let's say this was 10, okay? It's not, or it's not always 10, but it's not. But let's do that. And this is a 60-degree angle because this is an equilateral triangle, but I've bisected this, right? And that becomes a 30 because it splits the vertex angle here into 30 and 30, right? And so I've got a 30, 60, 90 triangle, right? So this is 10 cut in half, of course, because isosceles triangle will bisect the base. Becomes a 5, and then that's the opposite the 30, that's the short leg, and opposite the 60 is the long leg. That is the short leg times radical 3. So this becomes, right, 5 radical 3. Some real basic 30, 60, 90, right, area of a equilateral triangle. If you ever had to find the area of an equilateral triangle with a base of 10, right, it would be 1/2. So the area is going to be, right, 1/2 the base, right, 10 times 5 radical 3. Okay, but the important thing here is the relationship between this and this, right? So this 5 radical 3 is basically 10 divided by 2 times radical 3, right? So it's the base times 2. I'm sorry, divided by 2. I said times 2. It's the base divided by 2, right? That's what the 5 is, times radical 3. Right? So basically, the height is equal to radical 3 over 2b. The height is equal to radical 3 over 2b. Okay, good. So the volume, careful, we're not doing area, we're doing volume. The volume of this slice here, right, is 1/2 the base, right? That's the base, times the height, but I'm not going to put the height, right? And then times the thickness, don't forget that, which is dy in our problem here, not dx. So this height, I'm not going to use h, I'm going to use what? Radical 3 2b, right? So I'm going to put radical 3 over 2b. Actually, I don't want to put it there, right? I want to put it down here. Radical 3 over 2 times the base, right? So depending upon which part you're doing, because there could be minus 0, right? But in this, the way I'm looking at it here, right, this is going to be, and I'm going to have trouble fitting this in here, so we'll see what happens. Cube root of y minus ln y, right? And then that's the base, and then times the height, which is that times that. So I'm going to leave the radical 3 over 2 out here, right? Little crunch there, but right, times radical 3 over 2, and then repeat it, which of course is just squaring, which would save you a lot of work, right? Okay, So that's it. And by the way, this is a dv, not a v, because this is the volume, differential volume. There's our dy. And then all you're going to do is you're going to integrate that from 1 to whatever we said c was, I think it was. And then you're going to have to do this plus, right, the integration from 0 to 1 with the same thing, but only minus 0 instead of minus ln y, and then work that out. But I'm going to actually leave that to you. I might edit in the answer later, but I'm going to save some time because this video is running way too long. Okay, all right. Okay, this one we're going to sketch this. This would be probably a non-calculator problem as compared to the other ones where you absolutely need a calculator. All right, y equals x. Super easy. Square root of x. Right, well, the square root of what x we know goes up, and then it hits at 1, 1, right? Right, square root of 1 is 1. Plug 1 in for y equals x, you get 1. And so we're going to get something like this, right? Okay. So remember, it's a sideways parabola, right? Square root of x would look like, I mean, not square root of x, but square root of x plus or minus would look like that, right? But I mean, it's parabolic in shape is what I'm trying to say, right? Of course, it goes on like this forever. But that's all we care about is this region here. So the area bounded by those two, which of course would include 0, 0. In the first quadrant is the base of a solid. A solid is formed by semicircles perpendicular to the y, x, and then we're going to do perpendicular to the y. All right, so the x one's easy. Find the volume, of course. Okay, so our cylinders look like this, right? They're coming out of the blackboard like this. Here's our thickness there, our little dx, right? There's our radius is from there to there. And of course, this is our diameter. That's not our radius, that's our diameter from the top to bottom. So there, right, if you move this, it's right there. If you're looking at a helicopter view, right, there's my, that's my, my taco shell, right? My half cylinder right there from top to bottom. That's the diameter. That's the main thing. Okay. So we know that the volume of one of these taco shells is, right, a half cylinder. So it's a half pi or pi over 2 r squared, and then of course dx, infinitely thin. Well, this would be dy for part B, right? For part A, it's dx. Okay, and then what is this radius? Well, the radius is half of what I've shown you here, right? Because that's the diameter. The diameter goes from top to bottom, right? So the diameter is square root of x minus x, right? But it's over 2 because that's the diameter. The radius is over 2. So remember there's 2 is inside this parentheses here. All right, so for this one, I'm going to leave the 2 in here just to show you a different way to do it. But of course, you can pull that 2 out as an 8 because it's going to be squared as a 4 in the denominator. So this would be pi over 8 integral of radical x minus x squared, okay? Don't be fooled that the radical x is smaller than the x, right? That only matters after 1, but between 0 and 1, right? The square root of a decimal is bigger than itself, right? Like decimal, I mean a number be less than 1 and greater than 0. Okay, so let's integrate this from 0 to 1. All right, math 9. Actually, no, we're not going to make that same mistake we made before. Sorry. We're going to do pi over 2. Right, times, don't be fooled. The calculator doesn't care that this is not in the denominator, even though it looks like it's in the denominator. Right, a lot, like if you divide 4 by 3 pi, a lot of people forget to put parentheses around the 3 pi and it'll multiply. This is still going to multiply pi over 2 by whatever we put here, okay? Math integral . 0 to 1. Okay, I need a parentheses here because I'm going to square this thing. Radical x minus x. Now we got a problem with this divided by 2. So I'm going to actually need, yeah, see, it's better to pull that 2 out because this is a little messier. I've got to group that numerator, right? Oh, actually, I guess the squared will take care of that. Oh, okay, yeah. Yeah, this will be fine. Then I can just do divided by 2 like that. It's already grouped when in its squared. Oh, actually, but then this 2 has to be inside the squared too. So I'm going to cheat a little bit here and I'll put a 4 rather than going back and editing it and right. But of course, when you square that divided by 2, it becomes divided by 4 just because I'm lazy. But obviously, you could have put radical x minus x in parentheses, then divided it by 2, put that in parentheses and square it. You can see how messy this is either way. So it's probably better to do the pi over 8 method I showed you before, but this should work fine, of course. Okay, that looks really, really, really small, but that's not going to bother me too much because that's a really small region, and we're talking about baby little taco shells, right? So I'm not worried about that. That seems good enough. So 0.013 is rounded to the nearest thousandths place, okay? All right, and then for B, I'm going to go a little faster with B. So B, nothing crazy going on here except for 2 major things, right? 2 major things. First of all, they're going this way now, right? It's a dy problem. These are dy problems. We're doing this way. So my dv is going to be, right, 1/2 pi 1/2 pi then we're going to do r squared, of course, dy. Now, my first of all, it's going to be divided by 2 because it's a diameter, right? But my diameter now, if you turn your head to the right, is, right, this is the upper and this is the lower, right? That's the lower, that's the upper, because it's a dy problem. We're going to put everything in terms of y, which means I need to write x equals. So I'm going to take this one, which is easy. Of course, that's just x equals y. And this one, of course, is going to be what? X equals y squared. Okay, but my upper has now become the line, the linear function, and my lower is the parabola, right? It's actually the square root function in our perspective here, but it's actually the left-hand side of a parabola in the other direction. So we're going to turn our head to the right 90 degrees, and we're going to consider this x-axis to be vertical, and that positive x-axis to be positive vertical, meaning everything to the right is above, and everything to the left is below. So that's why the red line here is the upper function, and the parabola, the blue parabola, which is covered by purple, but the blue parabola here is lower. So I need to do upper minus lower, and that will be my diameter, right? My diameter. So upper is y, and lower is y squared. Okay, a little confusing there, but that's for the perpendicular to the y-axis, find the volume. Okay, now I'm going to integrate both sides to give me my volume. And luckily it's 1, 1 here, so I don't care. Like, it's not going to change. Don't be fooled. These are y values now. These are y values now. But it's luckily for us 1, 1. The y value and the x value are the same at the intersection points. So it's still 0 to 1. And then we're just throw this in our calculator, which shouldn't take too long. So I'll do it for you to check your work. So same. Actually, we're gonna let's do the pi over 8 thing this time. Let's pull this 2 out. Let's do this. I don't want to go through that again. Let's take this 2 out as a 4, which becomes an 8 when multiplied by this 2 in the denominator. So that's going to make our lives a lot easier. I'm just going to do it. I think you'll be able to follow me here. So let's do pi divided by 8. Save ourselves a lot of hassle. Times math, F-N-I-N-T, 0 to 1. Remember, this is still y's, though, even though it looks the same as the other problem. This is y's, right? And then we're going to square that radius. Well, actually, it's the diameter technically, but we have to use x. We can't. There's no y here, so it's going to be x. Don't be fooled. We're still doing everything right. Squared. So I got to close this and square it. Okay, there it is. And then, of course, my thickness dx. So let's put an x there. Okay. think that's right. And yeah, I'm expecting small volumes here. So that equals 0.013. Yep, that's it. Okay, last one, revolve about x equals -1. So this is a vertical line, so we're gonna have dy problem here again. This is a revolution problem though. Let's see where our shaded region is radical x plus 1, y equals x, and y equals 1. So it's this region here. Although I'm gonna draw my shade the other direction because it'll help you see better maybe. Okay, so this fin, if you would think about it like a fin, is gonna revolve like this about the y-axis, right? And so my cylinder is going to go off screen here, right? But the right side of the cylinder would look like this. Okay, but it's going to go off screen. And here is my radius of that cylinder, at least my outer radius, right? There's my outer radius. Okay, so a couple things we've got to do like before. We've got to take this function and turn it in terms of x, right? So I'm going to get y minus 1 and then squared equals x. Of course, the other one's easy. That's y equals x. Right? I should have put it the other way. I should put, let's not confuse you. It's x equals y. Just put the x on the right side. On the left side, excuse me. And keep the y's on the right side. Okay, so I changed this function here in terms of y. I've changed this function in terms of y, which is just a silliness. And of course, y equals 1 is not going to be one of our functions. It's just going to be our boundary, right? It's going to be our integration boundary here. So what I'm doing is, right, I'm taking cylinders like that cylinder and of course this cylinder here, off screen a little bit, and then all the way up to this cylinder here, right? So I need to represent all of those cylinders. I'm going to erase them just because they're taking up a little screen area here, okay? But that's what I'm basically doing. So what I need to know for this outer cylinder that goes all the way like this, right? Goes off screen here, is I need to know what is this radius, right? That's my outer radius. So if you turn your head to the right, x is upper, right? Positive x is upper because we're doing things in terms of x here. We're doing functions named x in terms of y, to be clear. So this is the upper function, and this is the lower function, at least for our solid figure, right? The outer. No, I'm doing it wrong. Sorry. Let me fix that. Sorry. For the outer function, the upper is here, excuse me, and the lower is our revolution line, right? That's our lower. Okay, because that is this rate right here. You can see this R goes all the way to the revolution line. Okay. Later, when we do the subtraction part, right, the air part, that's going to be our inner radius, right? And for that one, this is going to be the upper, and the lower stays the same. Okay. So if you follow the other problem, I'm not going to spend a lot of time going over this theory with you because I did this in the other problem we did earlier. But right, basically, right, the book will always tell you we're going to do this. We're going to do r squared. That's the outer one minus the inner one. I think they use small r, whatever, r1 or r2, whatever you want to call it. Right, dy in this case. And then, of course, this is going to be pi, and this is going to be integrated. In our case, this is going to be integrated from what? Well, 1 to that intersection point. So we got some work to do there, right? 1 to some, we'll call it d. All right, our intersection point. But, you know, basically that's what we're doing. And, of course, this capital R is the green, right? The upper minus the lower here. So the blue minus the purple line. And this baby R here is the red minus the revolution line. Again, in class, I usually do this as 2 separate integrals, right? All right, so but we still have some work to do. We've got to find the y value of this intersection point. Very important. I don't care about the x value. I really need to know what the y value is. Don't care about that. So let's put these two functions in our calculator. We don't have to convert them to do this, right? In other words, I can leave them in terms of x. So the first one was radical x. Okay, and the second one, radical x. Actually, no, I'm just thinking out loud here. I want to Oh, well, it doesn't matter for intersection point, but it will matter. It won't matter later. Okay, whatever. Radical x, and of course, no, sorry, radical x plus 1. Yeah, sorry, I missed that. Ugh. All right, we're going to start that again. All right, there we go. Radical x plus 1 and x. Okay, let's quickly graph these, find the intersection point. Yeah, that looks like our picture here. Yeah, it's just that there's a line. We don't have a green line for y equals 1, right, which starts there, but that's okay. All right, so second, calculate intersection. First curve, second curve, don't care. Even the guess, we don't really care because I think it's only going to intersect here, but we'll move over to there. Okay, so the y, oh, they're both the same, right, because x equals y, of course. So in this case, it didn't, we could have used either one. So anyway, d, go back to the screen, d is 2.61803. Okay, great. Let's define our R. That is the upper minus lower of our outer radius. Okay, so that's going to be y. This is the line x equals y. So it's going to be y. So pi integration from 1 to d, which we defined, of course. And then this is going to be, right, y minus the revolution line, which is -1, right? Revolve about x equals -1. So y minus -1. Y minus -1 squared. And then the inner radius, right, for the air, we're subtracting the air here, is this red, right? The red upper minus lower. This radius here, that's the air. So it's going to be the y minus 1 squared. So I'm going to be super, I need a little more room here. So that's why I'm hesitating. I think I'm going to need a little more room. Y minus 1 squared, right? Remember, don't forget this whole thing is squared, right? As you can see here, right? And then minus -1 also. All right, and that should work just fine. I don't have these functions entered in to here, right, in terms of y, so it's going to be a little ugly, but we'll do it anyway. Might have been smart to do that. Okay, so I'm going to multiply by pi first, so I'm going to do second pi times the integral from 1 to 2.618. If I had this stored, I could use d, right, but I can't. So pi times the integral from, oh, by the way, I don't want to be sloppy here. I'm going to be sloppy here. I am sloppy here, but this is dy, of course, right? And this is volume equals, as is this. Okay. All right, so, you know, super careful here. I'm going to use parentheses inside of all this, because that parentheses is just for the dx, right? That's just for dx. I know it's dy, but the calculator can't handle that, right? So we're just going to use x's wherever we're using y's, but it's the same integral. It's not going to change anything. Okay, so parentheses y minus -1. Now, of course, obviously, I'm just going to make it +1. Again, I'm typing in x because there is no y key, right? Okay, x plus 1, and then of course that's squared, so be super careful there, right? Okay, now outside of that is minus a new parentheses. Okay, now you need another parentheses because this function happens to be squared that we're typing in, right? So there's another parentheses, be careful, and then it's x minus 1, close that parentheses and square it, and then we're down to the, right, now we're down to this -1, which is of course +1. So +1, close that parentheses and square it. So that's a little bit of an ugly type in there, but that's it. If you look carefully at what I did there, other than x is y, right, that pretty much matches it. I hope so anyway. dx, and we had the pi in the beginning, so we don't have to worry about messing that up like I did earlier. And boom, there we go. All right, so the volume is equal to 20.295. Okay. All right, I'm not going to do the base of the solid semicircle. Maybe I'll post just the answer here. It's going to be, just super, super quick, though. It's going to be, right, the semicircle is going to look like this. I'll do this in blue here, maybe. Semicircle is going to look like this. Okay, you've got your thickness there, which is a dy. Upper minus lower is going to be blue minus red, right? But that's the diameter, so don't forget to divide that in 2. And then integrate it, of course, from 1 to, oh, did I do 1? Yeah, I did do 1. Okay, 1 to 2.61803. Right, so again, because you would have had to do this problem twice if this was a free response problem, it would have made more sense to put the functions in the y equals key. Just remember, it would have been x equals, right? So even though you're typing in y equals something with an x in it, right, you'd be typing in this function here, right? So in the calculator, it would read y equals parentheses x minus 1 squared, but you would still be typing this exact thing in. So the calculator confuses you a little bit with that, or could potentially confuse you a little bit with that. All right, I hope this helped. I will see my seniors tomorrow, but for anybody else watching the video, I hope this helped you out.